Good afternoon. My name is Rachel Meidel. I am with the Baker Institute for Public Policy at Rice University, and I'm a fellow in energy and environment at the Center for Energy Studies. And I appreciate the invite to come speak here this afternoon. And what I thought I'd discuss today is circular economy, waste management, and the energy transition, and talk about some of the policies and practices that are going to be needed in order to enable a sustainable and circular future. And sustainability is a critical investment if we want to migrate in this direction. Certainly, access to energy is critical for supporting a peaceful and prosperous population. And although the energy industry is currently dominated by fossil fuels, climatic and environmental impacts have reached levels where we have to diversify and think about integrating and transitioning to alternative energies. However, some of these new energy platforms come with their own set of challenges, where strategic policies are going to be needed in order to ensure a sustainable roadmap to better inform some of the challenges and opportunities that come along the way. Sustainability has, in recent years, become this crazy buzzword that is used liberally in a variety of contexts, and it has so many dimensions. Investors and consumers and other stakeholders are seeking to understand what a company's risks and opportunities are, and are increasingly demanding to know more about their performance related to sustainability. Companies and governments are becoming aware of the impacts, such as overseas sourcing and disposal, and ensuring suppliers and end markets uphold certain standards. And they're under immense pressure to account for sustainability in meeting global climate targets and integrating renewables and other low carbon technologies into their operations. But what's driving all of this? Well, they're being driven by the market, by shareholders and investors, by the UN Sustainable Development Goals, by international treaties such as the Paris Climate Agreement and the Basel Convention, and also by consumers' personal values. Most people equate sustainability as having an environmental focus. That's how most people think of it. Preserving future generations, attaining ecological equilibrium. But sustainability is far more than just assessing the environmental features. It's more than choosing presumed eco-friendly options or switching to renewables. As our perspectives globalize, it's being seen now for what it really is, a systems-level philosophy that integrates these three factors that you see here, the environmental, social, and economic aspects. And there's a lot of subdomains that include cultural, technological, and geopolitical variables, for example. Sustainability is that intersection, that equilibrium of all of these key factors. This is what it is, and it has to be assessed from a holistic, wide-angle lens, and it has to be looked at from a life cycle perspective. So when we think about sustainability, how do decisions that we make, for example, when it comes to exporting waste overseas, or integrating renewables into the mix, or even introducing an untested biodegradable plastic, how do they impact other parts of the value chain, both upstream and downstream, especially when we look at the social, environmental, and the economic factors considered? As our economy globalizes, it's become even more critical that we find ways to account for all the dimensions of what constitutes sustainability. Governments and companies, as I mentioned, they're aligning around sustainability goals more than ever before, and they're building these into their business models and strategies. The UN Sustainable Development Goals, these are a collection of 17 different goals, and they build off of decades of work by countries in the UN, and they're designed to be blueprints to sustainability. Corporate social responsibility are practices that outline how a company can contribute to social, economic, and environmental accountability. And that's accountability to itself, to its stakeholders, and also to the public. While corporate social responsibility is the efforts and commitments to sustainability, environmental social governance, or ESG, measures the performance of CSRs. So ESG refers to the three central factors in measuring the sustainability and societal impact of an investment of a company, and they're used by investors and shareholders to screen investments, and to assess a company's impacts so that they can better determine the future financial performance. You know, these days, evaluating and reporting solely on the economic performance of a company, it's just no longer sufficient for corporate and investor decision making in the world of sustainability. So in a world where we have to meet net zero CO2 emission targets, we have to think about what it's going to require. It's going to require a whole lot of infrastructure, a lot of land and other resources where the social, environmental, and other impacts are going to emerge. And many of them will emerge in developing economies along the supply chain. So understanding where those impacts are and how the institutional context influences sustainability across the value chain, that's going to be crucial for a fair, balanced, and equitable energy transition. So currently our business models follow a linear economy, and that is where we take materials, we make products, we use them, and then we dispose of them. Now, ideally, the goal is to gravitate towards circularity, where we design for durability, reuse, repair, and dismantling, but we're just not at that point yet. This is really the utopian future state here. And this is where sustainability solutions and the energy dialogue revolve around, and it's the circular economy model. It's gaining a lot of traction for achieving local, national, and global goals. And what it is a business model that keeps materials at its highest value all the way through its life. And it's regenerative by design. It replaces the end-of-life concept with restoration. It aims for the elimination of waste through superior design of materials and products and systems. Now, most circular economy interpretations focus on landfill diversion and material looping, and these both can result in trade-offs. With landfill diversion, you can meet that by incinerating or exporting agreements, and we've seen that with China's import ban that exposed that as a common practice. In material looping, although that can be really effective, it's only as good as the quality of materials that you're integrating back in. So for example, look at plastics. They can only be recycled once or twice before the quality degrades and it's eventually downcycled, and that has an end of life, which then is landfilled, incinerated, or exported, thus falling out of circularity. So more efforts, I would say, is needed in these areas, and that's methods for responsible extraction and upfront design and re-engineering so that a material at the end of its life can then be reinserted back into the economy with a second, third, or ideally an infinite life. Governments and companies should build this mindset into policies and practices. I would like to note, however, that a circular economy, as utopian and perfect as it sounds, and a notable vision, it's not, however, a silver bullet for employment, sustainability, and prosperity. It's only attainable if the economics, the policy frameworks, the geopolitics, and sustainability issues are all aligned and can be achieved across the entire life cycle. Decision makers in business and policy, they are increasingly confronted with a variety of challenges in search of sustainable solutions. And this is especially true as we face the current pandemic and as we work our way through the challenges of the energy transition and tackle global issues like plastic waste. We oftentimes look to policies, products, and technologies as solutions to help us achieve global climate and sustainability targets. So in this context, life cycle assessments are crucial to provide support in better integrating sustainability into decision making. And that's due to its systemic and cradle-to-grave approach. What it does is it evaluates the environmental impacts across the life cycle, all the way from raw material extraction, all the way down to final disposal. So this is a basic life cycle flow for batteries, and I'm simplifying for what is a very complex network here, but policy decisions should be informed by life cycle assessments. But current life cycle assessments are incomplete. Neither the internal nor the external economic aspects are within the scope of current methodologies. And the current ISO standard does not address integration of the economic analysis. So It also doesn't consider any social impacts, I'll note. And comprehensive life cycle assessments should be standardized, and it should be an industry best practice. Traditional life cycle assessments, they typically assess the environmental impacts, as I mentioned, and many focus primarily on emissions, but it should also include a full range of environmental impacts, such as effects on natural resources and biodiversity and ecotoxicology, because obviously the effects are going to extend just beyond the facility or the corporation or even a country. And this is important for solutions to be viable. Life cycle assessments, the results are oftentimes grossly misinterpreted because so much of it depends on the scope and how far up and down the value chain that it's conducted. Are you assessing just the product manufacturer, or are you looking at the product manufacturer and the use phase? Life cycle assessments in this sense can be useful for identifying bottlenecks for deficiencies and creating operational efficiencies within these boundaries, but they cannot be used to justify systems level sustainability or to even guide national or global policy decisions, as is currently being used in many of these cases. For comprehensive insight into the impacts across the entire value chain, it is really important that we look at each segment of the life cycle. And then we also have to keep in mind the raw materials extraction and final disposal. And one thing that we also have to take note of is the end-of-life management for how something is actually treated, because without that, it only leaves a partial picture of the true impacts from a life cycle perspective. Let me give you an example here of an end-of-life oversight in new energy technologies and why standardized comprehensive life cycle assessments should be required. So this is a picture of a 200 kilogram Chevy Volt lithium-ion battery pack. Propped on top of it at the left is a postcard size pouch battery, 288 of them, which make up the Volt battery pack. So for scale, a cell phone battery is shown at the center and an iPad battery at the right. Lithium-ion batteries are used in electric vehicles and smart devices, and 95% of them are incinerated. And there's a ton of valuable metals and other materials that can be recovered, processed, and reused, but very little recycling occurs today. Less than 5% in the US and EU, and much less in other parts of the country. China's annual battery waste alone is already estimated to reach 500,000 this year, and it'll exceed 2 million by 2030. Globally, we're looking at over 10 million tons of batteries that will become waste. Lithium batteries are very difficult to recycle. They're costly and they're extremely energy intensive. There are technical constraints, challenges in disassembly, economic barriers, logistical issues, and a lot of regulatory gaps. And because the lithium-ion battery industry lacks a clear path to large-scale economical recycling, battery researchers and manufacturers have traditionally not focused on improving recyclability. Instead, they've worked to lower the costs and increase battery longevity and charge capacity. And because researchers have made only modest progress improving recyclability, relatively few lithium-ion batteries end up being recycled. The International Renewable Energy Agency estimates that there was about 250,000 metric tons of solar panel waste in the world, and that's 2016. They also projected that this amount could reach 78 million metric tons by 2050. Solar panels contain toxic metals, heavy metals like lead and cadmium, and they can't be removed without pulverizing the entire panel. At the end of the life, solar panels are either exported, but the majority of them are landfilled and some are incinerated. Today, recycling costs more than the economic value of the materials recovered, and that's why most solar panels end up in a landfill. There's also no national or globally harmonized regulations for managing solar panels at the end of life, despite them meeting the legal definition of a hazardous waste. So waste management, or the second life use of solar panels, is rarely considered in the early stages of development, if at all. Companies and governments largely don't contemplate this. And this makes it very, very difficult at the end of the life disposal and recycling phase. This underscores an unquantified waste problem that runs counter to what the alternative energy and the renewable industry is held up to be. And that's an ideal solution to combat climate change, an attractive investment for companies, and a job creator for the US. We have a glaring blind spot when analyzing the true environmental and social impacts of new energy technologies. What happens at the end of a product's life has a considerable influence on its overall sustainability score. So turning back to our life cycle assessment, what we're seeing is that end-of-life management is not factored into the upfront design of material or products. We focus more on the functionality, and this is a gross oversight, and it's counterintuitive to circular economy principles. Further, upstream developments, as in the prior examples that I just gave, they're not keeping pace with the needed downstream technologies and policies like recycling policies and infrastructure. And this leaves a massive gap in the sustainability and circularity profile. The greatest potential to steer technology towards environmental and social preferable outcomes exists at the earliest stages of technology development, and that's at the R&D phase. We need to connect the energy sector with the waste sector and increase communication and coordination throughout the entire supply chain and incorporate recycling, disassembly, and reuse into the R&D. It shouldn't be an afterthought. So this entire life cycle assessment process, it is very important because it unveils barriers along the supply chain, and these are going to be needed in order to transition to a true sustainable energy future. Let's move now to upstream activities in the life cycle and supply chain. The mining sector plays a key role in the energy transition. The technologies required to facilitate a transition, including electric vehicles, wind turbines, solar panels, and improved energy storage, they all require significant mineral and metal inputs and generate a lot of waste through its life cycle, and they have impacts across the entire value chain. Critical minerals represent half of the periodic table, but the US remains heavily dependent on foreign sources. The Interior Department released a report in 2018, and it found that 31 of the 35 minerals designated as critical are import reliant, where the United States doesn't have any domestic production and relies 100% on imports. Between 2014 and 17, 80% of rare earth element imports came from China, while the remaining 20% was originally processed in China. So China's been at this a while. They've been scaling up mining capabilities and rare earth elements since the 80s. And this has resulted in a near monopoly, both on the mining of rare earths and then the processing of the rare earth oxides into manufactured products. So this in and of itself ushers in political and national security risks, sustainability risks, and also trade risks. The map here to your right displays reserve quantities of 18 of the conflict minerals. And the size of the circles correspond to the relative global quantity of the country's reserves. And overlaid with that is the fragility and corruption measures. So what you see here are potential hotspots for increased fragility, conflict, and violence that result from mineral extraction. The geopolitics of conflict minerals is immense, and it is understudied in the context of sustainability and circular economies. Significant reserves of all of these identified minerals on the left are found in states perceived to be both fragile and corrupt. How minerals are sourced and how they're managed throughout its life, including the end of life, that's going to determine whether this transition supports peaceful, sustainable development in the countries where strategic reserves are found, or if it reinforces weak governance and exacerbates local tensions and grievances. Metrics such as mining, processing, smelting, trade, transportation, and waste, and the social, economic, environmental costs are currently unaccounted for when determining the sustainability of the energy transition to renewables. We need to quantify these to understand how a technology or a product that's being sold as a solution behaves throughout its life, as well as its impact on sensitive environments and population. What we might perceive as a solution that is technologically, economically, and environmentally feasible may not necessarily be transposable or socially, politically, or even environmentally viable in another part of the world, especially if it's a non-OECD or a developing economy. We have to keep those things in mind. All energy producing technologies have to be fabricated from materials extracted from the earth. So technically speaking, no energy system is actually renewable, since they all require the continual mining and processing of millions of tons of primary materials, and then the disposal of hardware that inevitably degrades and is landfilled. Absent any dramatic technological advances or an increase in the use of recycled materials, these inputs will come from the mining sector. All forms of green energy require roughly comparable quantities of materials in order to build systems that capture sun, wind, and water. So in all three of these cases, the largest share of the tonnage is found in conventional materials like concrete, steel, and glass, all energy intensive processes. Further, mineral mining and processing is also energy intensive and produces hazardous waste. The waste and other environmental concerns can certainly be addressed and managed responsibly, but there is very little evidence of that occurring in China, where most of the world's minerals are being processed. Even if the metals are mined in the US or elsewhere, China still dominates the supply chain. Most are then shipped to China for processing. So we have to account for the costs and the energy inputs of transport and processing and shipment back to the US or wherever the minerals and product manufacture occurs. We also have to account for the social injustices of many of the countries that have weak or absent environment, safety, and labor laws and operate in opaque and corrupt regimes. It's such a complex Byzantine and interwoven supply chain, but that is why having transparency of life cycle impacts are essential to systems thinking. For many of the technologies and products deployed on the market today, we don't even have insight into all the risks, uncertainties, and vulnerabilities on a systems basis. The challenge for policymakers is to devise policy frameworks that enable the three critical goals of energy security, environmental sustainability, and affordability and access, while the energy sector undergoes a fundamental transition. If current IEA forecasts are met, there will be over 3 million tons per year of unrecycled plastic turbine blades by 2050, and that's what you see there on the left. And then on the right, by 2050, under our current plans and policies, the quantity of solar waste, much of it currently non-recyclable, is estimated to be 78 million tons and will constitute double the tonnage of all forms of global plastic waste that we have now. And I'd be remiss by not mentioning how the global pandemic has influenced the economy, since so much of how we do business moving forward will drastically change. And you know, as we transition to renewables, it's really important to understand what this means for us now. And the pandemic, certainly, it has undoubtedly tested our resilience and highlighted our lack of preparedness and adaptability. And this is important because the ability to rebound more quickly can reduce the negative health, environment, and economic impacts. The pandemic in and of itself has also exposed vulnerabilities in our system, revealing shortfalls in domestic production of critical goods. It has uncovered our reliance on an enmeshment of offshore supply chains for critical minerals, and it has accentuated our dependence on foreign markets for end-of-life management of waste. I would say in some ways the crisis has raised the stakes for sustainability, and it's actually become a dry run for the sustainability agenda, and an opportunity for companies and governments to see how they can tackle an expanding range of challenges. There's a lot to be learned from all of this. I think we should approach this pandemic with renewed interest in resiliency planning and an opportunity for building more sustainable business models while strengthening US manufacturing supply chains. The supply chain disruptions, I think, will prompt brands to reevaluate, restructure, and transform the dependence on distant and global suppliers. And they'll look to ways to reduce primary production by improving domestic waste management infrastructure and perhaps moving towards advanced recycling technologies. A potential longer-term benefit might be a faster pace of reshoring of manufacturing, investing in the design of circular materials, and building more redundancy in supply chains. You know, while the crisis exposes all these weaknesses in existing operations, I think it opens the door for investing in innovative engineering and advanced recycling, and for companies to abbreviate their supply chains and make them more transparent and socially and environmentally conscious. The waste generated with new energy technologies certainly presents an environmental challenge, but as I mentioned, also opportunities to create value and pursue new economic avenues. But before we can actually achieve a circular economy, policymakers, industry, and stakeholders, we have to anticipate and plan for the massive influx of waste that will be entering the end of life and design systems to capitalize on the resulting opportunities. As countries strengthen policy frameworks to transform their energy systems, there are ways to address sustainable end-of-life management goals by establishing end-of-life management policies that will generate value and secure long-term socioeconomic benefits, such as material recovery through recycling, creating new industries and jobs, end-of-life standards specific to energy technologies, and the development of collection and recycling regulations, including recycling and treatment standards, and things like regular reporting and monitoring of waste system with amounts of waste produced by country and technology, and composition of the waste stream, and causes and frequency of system failures. Those things should be reported to provide clear estimates of future end-of-life waste volumes. And the other is expanding waste management infrastructure. Strengthening domestic capabilities and boosting the development of local recycling industries can certainly help maximize the value creation of end of life. Adapting management systems for waste adapted to the unique conditions of each country or region is important. But I think one of the most important things is coordination mechanisms between the energy and the waste sectors. This is essential for supporting end-of-life management. Also stimulating investment in innovative financing schemes. And then lastly, promoting ongoing innovation, R&D and skills development, and technological R&D coupled with prospective techno-economic and environmental analysis. And this will help maximize societal returns and minimize detrimental outcomes and avoid unintended consequences. So the takeaways here is that sustainability really is multidimensional, and it is critical as an investment for a just and informed energy transition. And it's more than just companies and governments switching to renewables. With sustainability comes a huge responsibility. It's a commitment to innovate. It's a commitment to supply chain transparency and its impacts across the life cycle. A commitment to strengthen domestic infrastructure and overall supply chain communication to better manage inventories and flows of products and information. It's a commitment from policymakers to design laws that are consistent with technologies and innovation, especially at the end of life. And it's a commitment to better inform consumers. As we journey through the energy transition with the goal of circularity and sustainability, we have to ensure we don't unnecessarily complicate and confound existing systems, or shift risks, or create additional environmental and societal setbacks. This will be an essential element in the world's transition to a sustainable energy future.